Okay, so we are going to start chapter 10. Chapter 10 is analytic geometry in 3 dimensions. I went back and forth trying to decide what would be the easiest way, since I can't teach you in class right now, how to get this information to you. And so I was thinking I could, like I did the review page, I could write it out handwriting, but the nature of this topic, there's a lot of drawing involved, and we know I'm not the best artist, so I felt like going with the PowerPoints where I can then kind of talk to you and explain stuff as we go through. I think that might be the best route for this chapter. So our first section is kind of an introduction to the three-dimensional coordinate system. You can feel free to take notes on what's going to help you. So if it helps you to print this PowerPoint, I'll include the PowerPoint as well, or just to kind of watch it and hope that everything makes sense. Okay. So for this lesson, we're going to plot points, find distances and midpoints, and then we're also going to look at spheres. Okay. So you can read all of this, and like I said, I'm going to attach the PowerPoint, so I don't need to read the slides to you. Basically, I want to kind of explain as we go through some of the practice problems. So we will go. So this is why I think having a PowerPoint for this chapter is a little bit better than me hand drawing this. So a three-dimensional coordinate system. So we're taking what we would normally have as just x, y, and now we're adding the third dimension of z. So you can see in this illustration here, we have 3 different intersecting planes. So we're going to talk about what kind of space that creates and how do we find the different aspects of the space. So how do we find a point? How do we find distances? So there's three planes, the xy plane, the xz plane, and the yz plane. And then if you can visualize, and we'll go back to, there will be a picture here in a second where you can see instead of like just the x and the y axis creating 4 quadrants, we now have 3 planes that are intersecting, so it's actually going to create 8 different spaces, which we call octants. And the one, like when we look at the picture, the one that's closest to us, that's going to be the positive octant, where x, y, and z are all positive values. So there's 2 different ways you can look at a three-dimensional coordinate system. One is a left-handed orientation and one's a right-handed orientation. We are going to use the right-handed orientation. So here's an illustration of that. So every time that you're drawing points or you're finding distances or you're sketching a picture of this, you can kind of visualize that your thumb's pointing up, that's the Z direction. The X is kind of coming out towards you, and then the Y is going to be to the right. So this is the orientation that we will stick with for this whole chapter. So this is a good illustration of the 8 different octants. So you can see it's kind of a cubic space because we're now in 3 dimensions instead of just a 2-dimensional space. So octant 1 right here, where that cube is like coming out at us, that is going to be where x, y, and z are all positive values. So example 1, so this is one of the things that we need to do for this section, is to plot each of these points in space. So again, I'm going to attach this PowerPoint so you can click through this at your own pace and look at different things, but so we're going to kind of just talk through this example together. So the first point is 2, -3, 3. So that means our x is 2, our y is -3, and our z is 3. So if you're thinking back to those 8 octants, we start with the one that's facing us, that's octant 1, okay, and then we're going, if you think of that right hand rotation, so that would be 2, 3, 4. So this is actually going to be right here in octant 4. So this is 1 over here to 2, 3, and then 4. Then 5, 6, 7, and 8 are going to be the lower 4 octants. So if we look here, you kind of have to, this is the art piece of this, you kind of have to be able to draw a 3-dimensional cube or rectangular prism to find the location of the spot. So if we start here at 0, 0, 0, we know that positive 2x is going to be coming out towards us into two spaces. Negative 3y is, oh, my mouse is delayed. Okay, so here's our y. This is going to be 1, 2, 3 in the y direction, and then positive 3 for z, so it's going up 3. So if you're sketching this, you're going to kind of make that shape, that three-dimensional shape, so that you can know where to place that point to negative 3, 3. These are the other points that are placed, so you can kind of practice with that. You could kind of sketch it and then double check with this to make sure you have the correct location. Okay, so distance and midpoint formulas. So so one way to find distance would be to do the Pythagorean theorem twice. So if you look here, so we're trying to find the distance between x1, y1, z1, and x2, y2, z2. So this point right here to that point. Well, we have a x distance and a y distance, but then we would need to find that diagonal. So we could do the Pythagorean theorem with one triangle. Then that allows us to find out what the base of the triangle is that's including the z direction. So we could do two different Pythagorean theorems to find that distance. An easier way to think about it is this formula right here. So basically, you'll notice it looks very similar to the distance formula if we're just in two dimensions, but we're adding that z aspect to it. So distance formula is the distance between the x's squared plus the y's squared plus the z's squared, and then we take the square root of it. So an example, we're finding the distance between 1, 0, 2 and 2, 4, negative 3. So we would use our distance formula. We would plug in, so 2 minus negative 3. Oops, sorry. Oops, nope. So x is 2 minus 1. That's where our x is. Then 4 minus 0, right there. And then negative 3 minus 2, right there. Okay. So then those values, 1, 16, and 25, we add those together. We get the square root of 42. Sorry. Okay. So that's how we find the distance formula. So then also midpoint. So the midpoint between 2 points in 3 dimensions, you'll notice the similarity between the midpoint formula with 3 dimensions and 2 dimensions as well. So to find the midpoint, we add the x values divided by 2, adding the y values divided by 2, and adding the z values divided by 2. This is the same as what we did in 2 dimensions. So our example, we have 5, negative 2, 3, and 0, 4, 4. So we would just take the 5 plus 0, divide that by 2, and we get 2.5, or 5 over 2. We take negative 2 plus 4, we get 2 over 2, which is just 1. And then we take 3 plus 4, which is 7, divided by 2, which would be 3.5, or 7/2. So you can see here's an illustration. So you can see those 2 points, and then the midpoint falls right directly between those. Okay, so the last thing, the last main topic of this is the equation of a sphere. So if you can think of a circle in 2 dimensions and then expand that to this idea of a sphere. So a sphere, here we have a picture. Our center is at HKJ, and then we have a radius r. So if you think of how a circle is from the center point, the same distance all the way around, a sphere is going to be r distance from the edge all the way in every direction, all the way around. So we're going to connect this idea of the distance formula, and you're going to see a lot of similarities between the equation of a circle and the equation of a sphere. So the standard equation of a sphere is x minus h squared plus y minus k squared plus z minus j squared. So this should look familiar, equals r squared, so our radius. So if we cut out that z minus j squared, this is going to be the same equation as a circle. So we're not really adding a huge new idea, we're just adding that third dimension. So, and that's what this says. Notice the similarity of this formula to the equation of the circle and the plane. So we just are cutting out that z portion. Okay, so an example, find the standard equation of the sphere with center 2, 4, 3 and a radius of 3. Does the sphere intersect the xy plane? So using our equation, we're going to plug in 2, 4, and 3 for HKJ. So there's the 2, 4, and 3, and we're plugging in 3 for the radius. So here's our graph of this. So we have the point 2, 4, 3. We know the radius is 3, so you're imagining that it's going out 3 in every direction, both x, y, and z. And it says, because the sphere has a radius of 3, you can conclude that it does not intersect with the xy plane. Because if you think about here, so we have an x value of 2, a y value of 4, and a z value of 3. So if it's 3 away, then it's going, or sorry, did I say does intersect with the xy plane. So so this right here, it's touching that xy plane. So here's our x, here's our y. So it is touching that plane, if you can imagine that as a flat surface right there. So it's exactly touching it. It's not crossing it and going below. But now I can't remember how I read that. Sorry. So there's that. Okay, our last little bit is to note that the surface points satisfying the equation of the sphere are surface points, not interior points. So what that's meaning is that the solution points are not the points that all occupy the inside of the sphere, it's the surface of the sphere. So so if you can think of a plane cutting through a sphere, that's what we're going to talk about next, which it's the intersection of a plane and the surface, which is called a trace of the surface. So we're going to look at the trace of a sphere. So the xy trace of a surface would be the xy plane and how it intersects with that three-dimensional object. So we're going to sketch the xy trace of a sphere given by this equation. So this one would have a center at 3, 2, -4, and a radius of 5. So what we have to think about is that if we're trying to find out how the xy trace, it means that we're talking about just the xy plane. So what's true, if you think back to when we found intercepts by plugging in 0, that's what we're going to do here. We're going to find basically the xy plane by plugging in 0 for z, because that's what is true for that xy plane. So we would take the 0 and we're going to plug it in right here for z. So when we do that, then we get x minus 3 squared plus y minus 2 squared plus 16 equals the 25. Subtract that over to the other side, and then you'll notice we have this equation. So this equation should look familiar because it's a circle. So that means that the intersection of the xy plane and a sphere is, this particular sphere, is going to be a circle. So if we look at this, so this is a visual piece of what we just did. So here's the sphere that we were looking at, and this right here, this circle, is the trace, the xy trace, because if you're imagining that xy plane is like slicing into the sphere. And so it's slicing in, it's creating a circle, which has that equation. Okay, so that is it for this lesson. Like always, please comment or email me if there are any specific questions when you're working on the homework. Or if anything in this video didn't make sense, and I can do whatever I can to try to explain it in a different way, or write out some examples by hand, or whatever I can do to help in this different way of learning that we're doing right now. Okay, thanks.